Welcome to part 2 of lecture 6 on gamma decay for chemistry 418. Lecture 1 covered the topics shown here, and for lecture 2 we're going to cover Moessbauer spectroscopy. In this lecture we're going to discuss Moessbauer spectroscopy, which uses gamma emission and absorption to determine something about the chemistry and the chemical information about the compounds that contain the radionuclides. In this lecture, we're going to discuss the principles of Moessbauer spectroscopy, the conditions necessary, fundamentally you need solids, and something about the spectra that results. The basic principles of Moessbauer spectroscopy involve nuclear transitions. We have emission and absorption of photons. So it can be analogous to UV spectroscopy, where solutions can absorb photons that give us information about the chemistry of those solutions. Sometimes because of this emission and absorption of gamma rays, this is called nuclear gamma resonance spectroscopy. The only suitable sources for Moessbauer spectroscopy for the photon emissions are isotopes. The emission from an isotope is essentially monochromatic. Wavelengths are defined by the excited nuclear states. However, they can be tuned to a small degree by the Doppler effect. So if I have a source or a sample, and the source and sample are moving towards each other or away from each other, that Doppler effect can slightly shift the energy. And fundamentally, that's what we're going to exploit in Moessbauer spectroscopy. Sources and absorbers so sources and samples are vibrated. The spectra is recorded in millimeters per second, and you can look at the amount of the photon that passes through the sample as a function of the vibration, and you'll see that there's variations, and we'll use that to describe the chemical composition of the sample that contains the radionuclide. On this periodic table are highlighted elements or isotopes of these elements that can be useful for Moessbauer spectroscopy. Again, we should go back to what we discussed earlier when this is a review of recoil. We discussed that gammas can induce recoils in nuclei. Now, Moessbauer spectroscopy works only on solids. And if you, within this case, the recoil can be observed in the solids, and there's a potential where the entire lattice vibrates, not just the nuclei that was emitting the photon, but that vibration is sent out over the entire lattice, so the solid recoils. This is called recoil-free. Within this, there's a relationship between the energy, the velocity of the nucleus, speed of light, and the direction of the motion of the nucleus and the emitted photon. So there's ways of characterizing some of these energies. We talked about the recoil has a specific energy, and we can vibrate the system and have a small perturbation on that energy. So with this recoil-free fraction, we can have a distribution of energies from the gamma, a transitional energy from the excited state to the ground state, and the recoil energy. So we can have a range of these energy differences. Nominally, these are very small, on the order of eV at room temperature. Now, this is due to the fact that when this energy from the excited state to the ground state occurs, some of the energy will be going to the photon, and some of the recoil goes into the lattice energy, or this lattice phonon energy. Since these gamma states are very short, there's Heisenberg's uncertainty principle comes into play, and there's something called a gamma level width, which is finite due to the uncertainty principle. And what this says is that even though I have a very defined energy of that excited state, I actually have a distribution of energy because of my lifetimes being so short. So what Moessbauer did, he looked at this as taking the total recoil energy into two parts, a kinetic and a vibrational component. And if the emitter and the absorber are part of a lattice, these vibrations can be quantized. They're based upon the phonons of the lattice. So energy can be transferred only if they're in the correct quanta. So the system can be quantized, and absorbances from the emitter to the sample to the absorber can be evaluated as a function of the vibration or the speed at which the sample or the absorber is vibrating. If the recoil energy is smaller than the quantized vibration of the lattice, then the whole lattice can vibrate. The mass then becomes the mass of the entire lattice. The energy terms, they go into the lattice phonon system. So, and since this lattice is quantized, it's possible to find a state of a system unchanged after emission. So these are some of the terms or the basis that allows this spectroscopy to be performed. So fundamentally, what one does, if I use a sample for something, especially an energy that's above 150 keV, nearly all events vibrate the lattice, and this will give rise to the Moessbauer spectra. There's a large recoil-free fraction. In other words, that's the fraction that doesn't vibrate the individual atom, but vibrates the entire lattice. Some of the experimental methods that are useful for Moessbauer spectroscopy include reduced temperature, because then the vibrational lattice reduces and the recoil-free fraction increases. So temperatures are usually pretty small. And if the gamma level half-lives are greater than 10 to the minus 11 seconds, this width is around 10 to the minus 5 eV, which can actually be achieved, this Doppler shift, at around 3 centimeters per second. Something else that is unique and important for Moessbauer spectroscopy is the fact that you're using a nuclear interaction to probe a chemical state. And this is because you have a probability of orbital electrons being found in the nucleus. This energy can be broken into a nuclear and a binding energy component. And this binding energy component can be worked out, this change in the binding energy component can be worked out here as a function of the excitation, the excited and the ground state wave functions. This change is defined as the chemical shift. So very similar to other techniques, other spectroscopic techniques, one can determine what the chemical component is by evaluating this chemical shift. There's also magnetic splitting. So this transition energy will include a magnetic component, and like other spectroscopic techniques, you can split this into two I+1 values, so very similar to NMR. You can get information about the magnetic splitting of the sample. The magnetic splitting, will give you information about the magnetic conditions of the sample. So fundamentally, the technique is performed with a source. For instance, if one wanted to look at iron 57, one can use a Cobalt 57 source. Cobalt 57 decays to this state. Photons are emitted. These photons are perfect for the excited state of iron 57. So the emitter would be a Cobalt source, and the sample would be iron 57. And an example of this would be, here's a Cobalt 57 source, would go through a collimator, these photons would strike the sample, and there'd be a detection. This detection would be based upon the vibration of the source or the sample, and we can look at an absorption. And I want to point out here that the absorption is on the order of a percent, so a very small amount of photons actually get absorbed. But as the velocity of the source, and here's the velocity in centimeters per second, we can see that there's a change in absorption. We could use this to evaluate what that chemical shift is, and by looking up on a table, one could determine the chemical shift would be correlated with a certain chemical condition. Here's another source, an example where Moessbauer spectroscopy is done on iron, where another collimator, a sample, the sample could be a surface, and detectors are off at angles. So again, you should see scatter. A decrease in scatter as a function of this vibration would mean that some of the photons have been absorbed by the materials. This was used on the Martian surface. The data is shown here. Here's the velocity of the source, the absorption lines. And what one can do is look at the from these chemical shifts, you can get an idea of what iron components. And this was important for looking at the total amount of iron 2 relative to total iron. And this gave an idea of oxidation on the Martian surface, which would give an idea about the presence of water. Moessbauer spectra can also be collected for other elements. Here's an example for neptunium. Here's an example of all the chemical shifts. So if you could record the chemical shifts, you could see what oxidation state and chemical form of neptunium responds to those chemical shifts. So you could get information about coordination number, oxidation state, and chemical form. And then here's an actual example of some data, some Moessbauer spectroscopy for this neptunium iron gallium compound that was recorded at 10K, and the relative transmission goes from 100 to 99.7%. And here's an example of the data. So with lecture 6 on gamma decay, we've covered a number of different aspects of gamma spectroscopy and gamma emission. There's a number of areas that were fairly in-depth, but some of the concepts and ideas that you should take from this lecture include trends in gamma decay. How does it come about? How is it different from alpha and beta? Fundamentally, gamma can be a result of a decay of either alpha or beta, where the parent goes to an excited state of the daughter. What are the energetics of gamma decay? The energy ranges. And what are the different types that we're going to classify as gamma decay? The most prominent is photon emission, but we also talked about internal conversion and pair production. The other two being common when a spin and parity change from a parent to the ground state would be a 0 plus transition. Since a photon has a spin of 1, you generally need that spin change to occur. We talked about transition probabilities, both electric, E, and magnetic, M, how they can be classified. And where does this classification come from? It comes from the fact that a photon is from electromagnetic radiation. So you should be able to understand the transition from the spin and parity from one state to another during photon transition, and how you can define that in terms of E and M transitions. You should understand something about angular correlations, fundamentally that they occur, and then what does that mean about something in the nucleus, and how are they measured? So we went into some details about angular correlation in the lecture, but a lot of that information was you should just view as background. And finally, we discussed Moessbauer spectroscopy, a concept and spectroscopic tool that was awarded the Nobel Prize when it was by Moessbauer, who was at Technical University of Munich. And you should understand how Moessbauer spectroscopy is used, and fundamentally how Moessbauer spectroscopy is similar to UV visible spectroscopy, except you're talking about nuclear states, not electronic states. Some questions that you'd expect to answer about gamma decay are posed here. For instance, if one looks at platinum 195, the ground state has a spin and of 1/2 with negative parity, and there's two excited states that we'll show here, one at 3/2 minus at around 99 keV above the ground state, and another excited state about 130 keV above the ground state of 5/2 minus. If we look at the beta decay of iridium 195, it populates primarily with 57% of the time this 5/2 minus state. The question is, when this 5/2 minus state is populated, which one is depopulated primarily from a transition from this 5/2 minus state to the 3/2 minus state, or the 5/2 minus state to the 1/2 minus state? The answer, and as you can see here, when you look at the data from the table of the isotopes, this is a relative intensity value. So you can compare 1.2 to 1.3. 1.3 being larger means that that transition has a higher probability, and the transition from the 5/2 minus states to the 3/2 minus state, spin change 1, is the higher probability. The 5/2 minus state to the 1/2 minus state is also relatively abundant in comparison, between 1.3 to 1.2. Although there's a larger spin change, there's also a larger energy change. And then another question is, what is the transition multipolarity of those states from the 5/2 minus to 3/2 minus and 5/2 minus to 1/2 minus? You could calculate that, or by evaluating the chart of the nuclides, or excuse me, the table of the isotopes. You would see that this transition, the 1.3 relative intensity at 30.8 keV, is an M1 plus E2 transition, where the 130 keV transition is just an E2 type transition. Other questions such as what's the spin of a photon? You should be able to review the notes and perhaps other courses for that. What gamma transition types is expected from a 0 plus to 0 plus transition? Photon, this is photon forbidden. Those types of transitions would be emission of an internal conversion electron, so the energy gets transmitted to the electrons and the orbital electrons, and they can be emitted. Or if it's high enough energy, above 1.02 MeV, you get an electron-positron pair. Another type of question would be classification of the multipolarity of gamma ray decay, for instance what's shown here for cobalt 60M, so the metastable state of cobalt, cobalt 60, 60M cobalt. This state is a 2 plus state to a 5 plus state, so the transitions would be 5 minus 2, which is 3, or 5 plus 2, which is 7. The same parity, so the E's are the even and the M's are the odd transitions, so we'd have an M3 E4, M5 E6, or M7 as possibilities. And as we learned, the lower value, so the lower multipolarity, is one that's most likely, and you could check in the table of the isotopes that this indeed is the probable transition, the M3 state, for the photon emission from 60M cobalt. You should also be able to describe Moessbauer spectroscopy, which was just done in the previous lecture, and also with the lecture we just completed, and also in the previous lecture we discussed angular correlations. How are they measured? By aligning the nuclei. Gamma decay yields are very important concepts that were covered in the lecture. These are important factors because often gamma decay is what's used to identify an isotope. If I can count the number of photons that are present and I know my efficiency for the detector, I can get an idea of how many counts there are of a photon that represents a given isotope. And if I know the yield of those decays that result in gammas, knowing that the counts of the photons determines the amount of isotopes that are there. So for instance, not every isotope will produce a gamma with a decay. The isotopes that are listed here are examples of 3 isotopes that do produce photons with the decay. However, the yields are not 100%. If you wanted to find information for all isotopes, there's a number of resources. This is a very good resource. This link, it's the Lawrence Berkeley National Laboratory data site. You can go to this link, select nuclide search, enter the isotope you're interested in, and it'll show you the gamma decay yields. So for instance, if we did this for zirconium-95, the data that you would get from the link is shown here. You would get energy and intensities in the decay modes. So for zirconium-95, 2 photons are observed with pretty high intensities. One photon at 724 keV, one other photon at 756 keV. The 724 keV photon has an intensity of 44.17%, while the 756 photon has an intensity of 54%. So this means that 54% of the time for this energy photon, 44% of the time for this energy photon, those energy photons are emitted those percentage of time for every decay. What this looks like, if you have, this is from the table of the isotopes, is our gamma decay scheme, where we have the zirconium-95 decaying by beta. 54% of the time it populates this state. 44% of the time it populates the lower lying state. You see these are both 7/2 states. Zirconium-95 is 5/2 plus, so decaying to a 7/2 plus, very reasonable decay. We can even see the log of T values here, relatively low, spin change of 1. From what we learned in beta decay, these are common transitions. They're excited, and these nuclei de-excite through the emission of a photon, and we see that the half-lives of these states are on the order of picoseconds. So these are on the order of 70 picoseconds each. You can also get the gamma decay yields from the table of the isotopes. So for instance, here's the gamma decay of zirconium-95 from going to the niobium-95, so it's really occupying, it's populating the excited niobium-95 state. And we can get the photon intensity by multiplying the numbers in these brackets by the value that's listed here. So 0.5446 multiplied by 100, that gives us our 54%, and 81.11 multiplied by this value gives us the 44%. We can also look for the data for americium-241, which decays prominently by a 59.5 keV photon. If we go to the Lund Berkeley site, we see that the gamma intensity is 35.9%. Comparing this with what we see from the table of the isotopes, here's the americium-241. This is a truncated table, and it decays 85.2% of the time to this 59.5 keV excited state. However, only 35% of the time this photon decay is observed, and the reason for that is even though it occupies this same energy level 58% of the time, it has 2 routes for de-excitation. 36% of the time, so that agrees with this value, it decays from this 59.5 keV excited state directly to the ground state. That would yield this photon. And then the remainder, another percentage of the time is listed here. You see it goes from this 59.5 energy state to a 33 energy state, and then from that 33 keV energy state to the ground state. So there's these competing transitions. Another example could be Cobalt-60, again from the Lund LB&L site. We get the data. We see that there are 2 intense photo peaks, each one above 1000 keV, and yields on the order of 99%. And what this looks like from the decay scheme, this Cobalt-60 5+ decays to a 4+ state, so with 99.925% of the time. There's a transition from this 2,505 keV excited state to a 1,332 keV excited state. So that's our first photon. That's this 1100 keV photon. And then there's this de-excitation from this about 1.3 MeV excited state to the ground state, and that's the second photon. So an example with Cobalt 60, you can actually get two photons, each one about 100%. So Cobalt 60 is an isotope that's actually readily observed by gamma decay. Another important concept covered in the lecture has to do with metastable isotopes. What exactly are metastable isotopes? Well, those are long-lived nuclear states. The gamma decay that result from these metastable states are called isomeric transitions. So you'll hear metastable states, isomeric transitions interchanged. What these are just excited nuclear states that decay by emission of a photon. One of the reasons that they're important is because technetium-99m, the workhorse of radiopharmaceuticals, is a metastable state. So provide the half-life of technetium-99m. This is something that you should be able to do. So if we look at the chart of the nuclides, this is the technetium-99m. This is technetium data, technetium-99. The technetium-99m, the metastable state, is to the left, and the ground state is to the right. So all of our data for the metastable state is listed here. The spin is 1/2 minus. And then if we were asking what's the half-life, well, the half-life is 6.008 hours. And again, this is something that you should be able to answer questions based upon the chart of the nuclides and provide data for metastable isotopes. Why do these isomeric states exist? Well, they have to do with one of the reasons that also influenced beta decay was changes in spin and parity. An example that we talked about in the first slide of this lecture on zinc 69. Zinc 69 has a metastable state that lasts 13.76 hours. That's because this nuclear excited state has a spin and parity of 9/2 plus, while the ground state has a spin and parity of 1/2 minus. So there's a large parity. There's a large spin change along with a parity change. This is forbidden to a large extent, so the probability that that exchange is large, and for that reason the half-life is long. And where do isomers exist? If you look at the chart of the nuclides, where would you tend to find isomers? They tend to be near magic numbers. From nuclear models, we'll discuss information related to magic numbers. For instance, the shell model. One of the magic numbers is 50. We'll see that, for instance, the element with a Z of 50, tin, has a large number of stable isotopes. That has to do with this magic number state. Indium has a Z of 49, and it's just looking at an example of some indium isotopes. You see from indium 110 to 115, every isotope has a metastable or isomeric state. When you've completed this lecture, please comment on the blog and provide answers to PDF Quiz 6.